Today we want to do a quick review of solving quadratic and simple rational function inequalities. Let's first recall the theorems of inequalities. First, if a is greater than b, where a and b are both integers, then a plus c is greater than b plus c. For example, if x is greater than 5, then x plus 2 has to be greater than 5 plus 2, and x minus 3 would be greater than 5 minus 3. The second theorem says if a is greater than b and c is greater than 0, that is, c is a positive number, then ac is greater than bc. So, for example, if y is greater than 2, then 3y is greater than 3 times 2, which is 6. On the other hand, if a is greater than b and c is less than 0, that is, if c is negative, then ac is less than bc. Note that in multiplying both sides of an inequality by a negative number, you must change the direction of the inequality. For example, if a is greater than b, then negative 5a is less than negative 5b. Lastly, if a is greater than b, then 1 over a is less than 1 over b. So, 8 is greater than 3. 1 over 8, however, is less than 1 over 3. So, taking the reciprocal of both sides of an inequality also changes the direction of the inequality. So let's look at some quadratic inequalities first. Find the range of values of x for which f of x, which is equal to x squared minus 3x plus 2, is greater than 0. Note first, in terms of the word used in the question, that word range, this has nothing to do with the images of a domain that are fed into a function. This simply refers to the multiple x values that make f of x, in this case, greater than 0. So we're just using the word range in terms of its normal English usage. When given the quadratic, first thing we want to do is check for factors. Can it be factorized? Please note that if you do not at first see the factors, check whether b squared is greater than 4ac, because of course you know that will tell you that it has two real distinct roots, roots if it were equal to 0. I say that because for the vast majority of cases, or every case I have seen, in a question such as this, the quadratic can always be factorized, or there are roots. Okay, the curve does not lie entirely above or below the x-axis most of the time, so check. So, rewriting f of x in terms of its factors, we get f of x is equal to x minus 1 in brackets by x minus 2 in brackets is greater than 0. This leads us to the critical values x equal 1 and x equal 2. These are also called the zero values. Please note that they are not called roots, since f of x is not equal to 0 here, but rather it is an inequality. So let's drop those two numbers, those two critical values, on a number line. I suggest that you do this every time, regardless of which method you use. I'm going to show you two methods, simply to make sure that you do not make a mistake in your mind as to which value comes first. In other words, which is to the left and which is to the right. We're going to divide our x values now into 3 distinct intervals broken by the two critical values. And we're going to do that so that we can create this little table here called a sign table. Sign as in whether the sign is positive or negative. So you see the first column is which interval of x are we dealing with? Are we dealing in this case with x less than 1, x lying between 1 and 2, or x greater than 2? Then we're going to look at the two factors of the function, x minus 1 and x minus 2, and we're going to look at the function itself. We want to look at what sign obtains. So when x is less than 1, x minus 1 will be negative. X minus 2 will also be negative. Negative multiplied by a negative is positive. When x lies between 1 and 2, x minus 1 is positive, but x minus 2 will still be negative. So f of x, the product of the two factors, will be negative. And in the last case where x is greater than 2, x minus 1 will be positive, x minus 2 will be positive, and thus f of x will be positive. Now, what are we interested in? We're interested in where f of x is positive, where it is greater than 0. The x values for which f of x is greater than 0, you notice it is where x is less than 1 and x is greater than 2. That means we have a disjoint range. So we are going to write our solution for f of x greater than 0 for x is such that x is less than 1, in our curly brackets to indicate that is one set, union the other set, x is such that x is greater than 2. That colon means such that, curly brackets, set of numbers. The thing is, f of x is a quadratic with a minimum point. How do we know it has a minimum point? Because the coefficient of x squared is positive. We also know that it's going to cross the x-axis at the critical values at 1 and 2. So why don't we convert that number line to an x-axis, put an arrow, say x-axis, and sketch our quadratic. At which point we know that f of x is greater than 0, or it is positive above the x-axis, and f of x, or y, is less than 0 below the x-axis, and of course on the x-axis, y is equal to 0. That's the equation of the x-axis. So in this case, we are looking for where f of x is greater than 0. Well, there it is. See, they're traced in yellow. So the curve is heading up on the left, and the range of values of x for that curve is for that part of the curve is x less than 1. And on the right-hand side, as the curve heads up above the x-axis, the range of values for that part of the curve is x greater than 2. Hence, we have the exact same solution. So you have a choice. You can use the sign table or use the sketch. You know which one I prefer? Sketch every time. Let's look at another example. Find the range of values of x for which 3x plus 2 is greater than 2x squared. Well, first, we need 0 on one side of the inequality. So we rewrite it as 3x plus 2 minus 2x squared is greater than 0. Then let's, make things tidy and arrange it as ax squared plus bx plus c. So there we have negative 2x squared plus 3x plus 2 is greater than 0. But also, why don't we multiply by negative 1 on both sides to just make factorizing a bit easier? So we have 2x squared minus 3x minus 2 is less than 0. Remember to change the direction of the inequality. Remember, respect the negative sign. Be careful. So we can now say let f of x equal 2x plus 1 in brackets by x minus 2 is less than 0. So we have factorized. That gives us our critical values of x equal -1/2 and x equal 2. There's our number line, making sure the numbers are in order. -1/2 comes before 2. Here we have our sign table with the 3 distinct intervals of the x values. So for x less than -1/2, both factors would be negative, which means the product of the factors f of x would be positive. For x lying between -1/2 and 2, we have positive by a negative gives us negative, and x greater than 2, everything is positive. So what are we interested in? We're interested in where f of x is less than 0. So that is the range of values of x where x lies between -1/2 and 2. But remember, again, we can sketch this. Quadratic with a minimum point. Let's get the quadratic up make that number line an x-axis. Where is it less than 0? There is the curve lying beneath the x-axis, and that's my range of values of x. So that implies that f of x is less than 0 for the solution set x is such that it lies between -1/2 and 2. Suppose instead of the question saying 3x plus 2 is greater than 2x squared, which took us all the way down to f of x equal 2x plus 1 into x minus 2 is less than 0. Suppose instead the question was not a strict inequality, but was rather a greater than or equal to. So there I've put in all the or equal to's. So what happens to our solution set? Well, it now has to include both -1/2 and 2. It has to include the critical values because f of x is equal to 0 at those critical values. And so that now is my solution. Let's look at some simple rational inequalities now. Find the values of x for which f of x is equal to 2x plus 1 all over x minus 1 is greater than 0. Please note, as soon as you see a rational function, you are immediately supposed to think of, hey, what are the restrictions on my domain? What values can x not take? Remember, you cannot divide by 0. So in this case, x cannot be equal to 1. For a rational function, the critical values are the 0 values of both the numerator and the denominator. So in this case, the critical values would be x is equal to -1/2 and x is equal to 1. There's my little number line just to make sure that things are in order. I'm going to divide my x values into 3 distinct intervals separated by the 2 critical values. And here's my sign table. We're going to fill it in exactly the same way. What happens to 2x plus 1 when x is less than -1/2? What happens to x minus 1 when x is less than -1/2? And then when I divide a negative number by another negative number, my quotient, the f of x, is positive. Likewise, the second row, I have a positive divided by a negative, which will be negative, and then all positives. I am interested in where f of x is positive, where it is greater than 0. So those are my two x intervals for which this is true. So f of x is greater than 0 for x is such that x is less than -1/2 union x is such that x is greater than 1. Now, how would we graph this? To use a graphical method, what we do is we say, let's multiply both sides of the inequality by the square of the denominator of the rational function. Why the square? Because a square is always positive and therefore it does not change the direction of the inequality. Were we to simply multiply by x minus 1, sometimes x minus 1 is positive, sometimes it's negative. That's not helping us. We want to ensure that the inequality remains in the same direction. So let's cancel and multiply by 0. Anything by 0 is 0. And we end up with 2x plus 1 in brackets multiplied by x minus 1 in brackets is greater than 0. So let's do sketch as we know. There's the number line again. It's a quadratic with a minimum point. That number line is my x-axis. Let's sketch my quadratic. By the way, you notice I have not put any y-axes in these sketches. Why? Because it doesn't matter. They're irrelevant to my solution. The value of the minimum point, irrelevant to the solution for these questions where all that is being asked is a range of values of x that make f of x either positive or negative. So there we see the curve lies above the x-axis for the range of values of x to the left of -1/2, which means x is less than -1/2. It also lies above the x-axis for the range of values of x where x is greater than 1. Same solution. please note, what was the first thing I said? I said check the restriction on the domain of that function. And the restriction on the domain was that x is not equal to 1. So double check your answer and make sure that x is equal to 1 is not included in that answer. And it is not. So we're okay with that. How about this example? Find the values of x for which f of x is equal to x over x plus 1 is less than or equal to 0. So again, the restriction is x cannot be equal to negative 1. Our critical values are the values of x that make both the numerator 0 and the denominator 0. So our critical values would be x equals 0 and x equal negative 1. There's my number line, and again, I have divided my x values into 3 distinct intervals. Here's my sine table, and here it is all filled in. So, f of x is negative for this middle row of the sine table, and for the range of values where x lies between negative 1 and 0. So notice, I have initially written my solution as f of x less than 0 for x lying between negative 1 and 0. You notice I've written it with strict inequalities. There's no equal to sign. Why? Because I need to think it through carefully, because it was a rational function with a restriction on the domain. The actual answer has to say where f of x is less than or equal to 0, as I've written in here. X can be equal to 0. That's fine. There's no restriction there. But x cannot be equal to negative 1. Therefore, this is my final solution. F of x less than or equal to 0 for x lying between negative 1, not including negative 1, lying between negative 1 and 0, but including 0. Okay? Let's check it out if we were to graph it. So we multiply by the square of the denominator on both sides. Neaten things up, cancel factors, multiply by 0. We get x multiplied by x plus 1 is less than or equal to 0. Same critical values, 0 and negative 1. Drop those on a number line. It's a quadratic. There we go. The curve lies below the x-axis for the range of values of x between negative 1 and 0, but x can equal 0. It cannot equal negative 1. Solid circle, hollow circle. So I have the same solution. F of x is less than or equal to 0 for x lying between negative 1 exclusive and 0 inclusive.